speaker of today's Lightning talks is Ryan States from Indiana University, and he's going to tell us about Milnor's invariants for knots and links in closed-oriented treatment. Thank you.
Great. Thanks to the organizers for the invitation to speak. So first, I want to tell you just a little bit about classical Milnor's invariants. So Milnor defined these in 54, and it's a sequence of inductively defined invariants for links in the three-sphere, which work like generalized linking numbers. So actually, the most basic ones just are linking numbers. And then there are these higher order linking numbers. And they're studying the images of the longitudes of the link in the lower central series quotients of the link group. So that's this group I have right here. And it was observed by Casson first, I think, but it's really a corollary of Milnor's work along with Stalling's theorem that these are concordance invariants. And so before I define these for knots and links and other three manifolds, I first want to mention that these are not interesting invariants for knots in the three-sphere. And really the deeper reason for this, other than the fact that you don't have a link to work with, is that knot exteriors for knots in the three-sphere all exhibit nice maps to the trivial knot exterior. So we can use the trivial knot exterior as a place to compare two knots. Links in the three-sphere or knots and links in other three manifolds don't have such a nice space. And you can actually view Milnor's invariants as obstructions to the existence of nice spaces like this. So now let me tell you how to get Milnor's invariants for knots and other three manifolds. We'll just stick with knots for this talk. So first I'll define these spaces XKN, which are homotopy pushouts of diagrams that look like this. This map right here is taking the knot exterior to some Eilenberg-MacLane space whose fundamental group is some sort of lower central series quotient of the knot group. So you should imagine Milnor's invariants might be coming into play here. And these homotopy pushouts come with canonical inclusions that I'm calling iota k sub n of the three manifold into this homotopy pushout space. And so in order to compare two knots, what we might want to do is compare these two iota maps that we're getting for the two different knots. So in order to make this comparison, I'll first require a little bit of algebraic information, namely some isomorphism of lower central series quotients of the two knot groups, along with some boundary information that I'm sort of sweeping under the rug here. And from this, I can get a homotopy equivalence of these spaces I've defined. And I can use this homotopy equivalence to compare the two maps of the three manifold coming in, and namely ask if it takes one iota map to the other. In other words, does this diagram commute up to homotopy? And so this gives us a sort of the first definition of an analog of Milnor's invariants in this sense. This is like a homotopy theoretic analog of Milnor's invariants. I take the composition here and I want to compare it to this map. And this might be a little dissatisfying because I'm just getting some homotopy class in a set. It's not in some homotopy group or something like this. So I could pass to homology and look at the induced maps on homology, apply them to the fundamental classes and take the difference. And so this can be viewed as a sort of homological way of comparing the two maps. This is this theta n invariant I've defined, which is like a group homology analog of Milnor's invariants. It turns out that it takes values in the third homology of this lower central series quotient group. So I have two invariants, right? This homotopy invariant, which turns out to be an invariant of concordance in the three manifold cross I. This theta invariant, which turns out to be an invariant of homology concordance, so actually concordance in a homology cobordism. And so I can actually define this one more generally for knots in possibly two different three manifolds, maybe homology cobordant three manifolds, make a similar definition that lies in the third homology of a group. So before I finish up, let me just mention that these invariants can be extended to links. There's some complications there, but they can be extended. And when you do this, you can recover Milnor's classical invariants. So for links in the three-sphere, these are equivalent to Cantor's link invariants, which are equivalent to Milnor's invariants. And also there's a nice relationship between links and their sublinks. And in particular, if I define the invariant for the empty sublink, I recover some recent homology cobordism invariants defined by Jae-Chun Cha and Kentor that they call Milner's invariants of 3 manifolds. Yeah, I think I'm probably about out of time. I'll skip to the end and just say thanks for listening.
Questions? So let's leave the questions for lunch, and thanks again. Should we take a 5-minute break?
Is there fresh coffee? Yeah.
Okay.
If anyone wants a cup of coffee, get it. Come back.
Okay. And